Hello. Uh, let's say, so I got a question for you. What do you think is harder than resisting the urge to add a new feature to your product or your project? Uh, have any guesses? Yeah, that's a good one. uh, but personally, for me, I think one of the hardest is to remove a feature that I have already added, especially after spending a very long time implementing it. Uh, and yeah, uh, I'm embedded software and hardware engineer, and lately I have been mostly working in the automotive sector. Uh, and simple things tend to have a flooded market, like forks, spoons, chairs, and power banks. And that is exactly why I started a project a couple of years ago, working on an open source power bank. Uh, and basically, the reason for that is because there's a lot of power banks, but open source version is non-existent. There have been a couple of projects, but they're usually not fully commercialized. And before I started this project, I have made a couple of commercial devices, and one of them is the smallest lithium battery charger, which I crowdfunded on Power Supply a couple of years ago, on Crowd Supply. Um, and this was actually a great project because it's a small product. It's easy to design, just to test the waters of crowdfunding. And some of the other projects I've made over the years is a supercapacitor charger, with a special feature being that it's configurable with jumpers and some like variable resistors, and it supports solar panel input. Um, Another project which I haven't commercialized but I have published is the DC power meter, which has 3 channels and supports up to 10 amps of current, and is compatible with the Arduino Nano and Feather ecosystem. uh, yeah, and the crowd supply was the great project to test how to do this kind of thing, because it was the first time I did the crowdfunding. And while the product itself was pretty easy to make, every other category, like for example testing, making like text fixtures, or developing the whole test system itself with the software and Python scripts, and labeling everything, you have to design labels. All of those categories have taken most of the time compared to actually making the product. And yeah, so that was a great way, and I would highly recommend you, if you haven't done any project on crowd supply, to take some small maybe device that already exists and add a new feature, and just try it out. And you might have noticed that uh, my projects are basically bare boards with no enclosure or any software, and the only user interface that there is are jumpers, which is kind of barely a user interface. And these kind of projects I've made without much of a stress as a side project together with my full-time job. So I wanted to make something a bit more ambitious. Um, and my goal was to stand out from this vast amount of power banks that you have on the market, and make it open source, make it configurable, and provide some interface like over USB or UART, where you can also collect some metrics. And there are a variety of the power meters available like this on the market, but they're kind of more of an add-on. And I wanted to have something that's like integrated in one piece. I also wanted to have modularity, which is great for like replacing the microcontroller with another one, or it's also great for doing repairs compared to having like a single monolith system. And basically, these are the features I wanted to have as the minimal starting point: to have two USB-C power delivery ports, some DC output, DC input, some GPIOs, and of course USB and UART for the communication. And initially I wanted to have it as a power bank. However, down the line I realized that including the batteries in the product is going to be a very huge pain, and even including the holders for 18650 batteries is not the kind of the risk I wanted to take, shipping a product like that, and then the user can basically put in a unprotected cell. And there have been actually a talk on Friday by Carrie Sundra, the health of putting a battery in it. And if you haven't listened to it, I highly recommend you watch the recording sometime after. So basically, with all of this, I have pivoted to making a power bank without a battery. So basically, the whole electronics, but the user has to connect its own battery, which also can support the smart battery, which is basically a battery which has SM bus, and SM bus is very similar to I2C. It's kind of specification on top of I2C, and a lot of I guess older laptops that have removable battery, all of those are smart batteries basically, and you can get a lot of off-the-shelf batteries that are also smart batteries. Yeah, they kind of look like this. And then the one on the left is a very popular brand, RRC, and they actually used in quite many products as an off-brand. And basically, it's a battery that has all possible certifications, and it's very nice to use it in your own projects because it's very safe, but it's a bit pricey. So this is the Rectangle 2, the project that I have been working on. And actually, the first sort of elevator pitch I had to do was at the airport security twice. In Europe, though, not in the US. And so it has, this is like the front panel, and it has like two USB-C ports with power delivery up to 60 watts. A DC output with configurable voltage and current limits, some GPIOs, and like I2C SPI, UART ADC, and DAC, like the standard stuff. And the back has the DC output, a USB port for communication, which acts as a USB device and provides virtual COM port, and also the battery connector as well. And for the display, I have used a Sharp membrane pixel display. It's monochrome. And the case is machined aluminum, and I've used KiCad and Fusion 360 like I guess the rest of the people. And the first lesson I think I've learned with this project is to start with the enclosure design and not with the PCB design, because the issue is that if you start with the board design, you usually tend to make just like a rectangular board, and if you try to design enclosure around it, you end up wasting a lot of space inside of the enclosure, because you have to find space for like screws to assemble everything, and you just have this large solution. So I had to redesign the board, and this was like one of the later versions. So you can see that the shape is different, and basically the corners are there to, or like the cutouts in the corners are to accommodate all the screws and stuff inside. Uh, Another um, yeah, so the whole case was CNC machined, and another limitation with CNC, it's kind of obvious, but it's the internal corners, because you cannot make straight corners, and generally, if you go below 4 millimeters or 1/8 of an inch, your cost is going to go up. But I still had to go below that for connectors. Uh, so one of the issues I have had is the display, because the display is rectangular and I didn't know what to do with it. And eventually I just made the rounded corners and I just have hidden the pixels behind, and I just kept using the pixels. And that also kind of gives it a more modern look, because nowadays we have like phones and stuff with the rounded corners. Um, um, Another um, another thing, let's see. Yeah, another issue I have had with the enclosure was after I ordered several batches of different parts, and you can notice that the surface finish, for example, for the faceplate and the rest is different. And that one I actually haven't realized that it was going to be a problem, but apparently there is no a good way of specifying surface finish that it's is exactly the same, and when you put two things together you can see the difference. And actually to this day I still don't know a way of specifying it to get the same thing, and seems like the only way to do it is to order everything at the same time. Um, and I have often found myself stuck with things for days, and the connectors was probably the longest I've been stuck with. And I've been looking for a power connector, and I pretty quickly narrowed it down to the barrel jack with the 5.5 millimeter outer diameter. But then later I found out, okay, you can have 2.1 millimeter inner pin and 2.5, and which one is more common? And yeah, who thinks that the 2.1 millimeter is more common? Can raise your hand. Or 2.5 millimeter? Okay, that's pretty interesting, because what I found out is 2.1 millimeter is more popular. Uh, and actually, what I was trying to find out, that was exactly before the ChatGPT, and I mean, it's hard to find it out. You don't have like a research on this. But yeah, if you ask ChatGPT today, it will tell you it's 2.1. If you look at all the devices like routers, all this network appliances and stuff like that, typically 2.1 is more common. And on top of that, actually, when the barrel jacks were introduced, originally the outer shell was positive, and only later it's changed to outer shell being negative. And you can still sometimes find devices where outer shell is positive, but mostly it's ground nowadays. Um, let's see. Yeah, and the battery connector, that one is probably the most difficult one, because there is no standard. There's kind of de facto standard, which is this XT60 type of connectors, but they only have 2 pins, so there's no support for SM bus. And then one of my first iterations was I decided to use the DSAP connector, because it's, I mean, you cannot go more standard than this, and actually you can get one from several manufacturers that support up to 5 amps of current. And I even made a prototype board with it, and basically I decided not to go with the solution because the connector is just too big for, I mean, this is like the size of the device. And also it looks really weird to have like basically COM port connector for a battery Um, so then I considered several options, like Molex Minifit is very popular, used like in PC, yeah, in the PC Power ATX. But that one was too big, so I went with a bit less popular Microfit, which you can see in the corner down there. But then I thought that one is also a bit too big, so I went with NanoFit from Molex as well. And that one I have, I'm using it. I decided to use that one, and it's down there. Uh, and yes, I also spent quite a lot of time choosing the board-to-board connector, and I settled for using the dual entry 2.54 millimeter one, because basically you can have like you can have a carrier board in the middle, and then you can have whatever you want on top or and on the bottom. And the solution is pretty compact for the price and how standard it is, which I really like. And at some point, I went too far with the modularity, and I don't know how many of you know what this is. A couple of you know, yeah. So this is a micromod system from SparkFun, which was introduced about in around 2020. And I thought that this was great for my project because basically the system uses M2 connector, which is commonly used for like Wi-Fi and older SSD drives in laptops. And the idea of the system is this M2 connector has a tight specification on like GPIOS, ADCs, and stuff like that. And and I made also like a prototype with it. But the problem was that it didn't really become that popular. It's very niche, and eventually I removed it from a project. And I would say one of the lessons for that is that you shouldn't use like a brand new technology unless you're prepared to take the risk that you have to redesign it. And yeah. And then the next thing. Uh, uh, yes, the next big thing was the screws, and I actually wasn't expecting that I would spend so much time choosing the screws because it's like, you know, it's just a screw. You just want to like put your enclosure together and mount some PCBs, and I needed two types of screws, like the countersunk and the cheese head, and I was basically choosing between the Torx and the Allen key. And I decided to settle for the Allen key because it's pretty cheap to include this, you know, this L-shaped driver together with your project. And yeah, subjectively, it seemed to me like it's more popular choice. I don't know. IKEA uses them everywhere. Uh, and I thought that it would end on that, but then it turned out that if you have M2 thread for both of the standards, the driver size is different. And what I found out later also is that the Allen key countersunk one actually doesn't list M2 thread in the standard, but you can purchase the M2 screws all over the place, and it's actually just a custom extension of the standard. And that was, and I only found it out after I already put everything into the project, and my goal was to use the standard screw, but I ended up using something that's custom, and like the takeaway from that is to basically not trust actually anything, because even if you ask ChatGPT, it will tell you that M2 thread is in the standard. So if you really want to make sure, you have to read the standard. Yeah, and the next one, does anyone know what this is? Not the coin, but the thing in the middle. Any idea? Yes? No. So this is a battery. It's the smallest kind of coin cell battery you can commercially buy. It's yeah, CR425. It's like yeah, the 3-volt lithium manganese battery. It has only 25 milliamp hours um, capacity, and basically this kind of battery I use for RTC clock. And it's very tempting to, when you have a device of like this size, it's very tempting to choose the smaller coin cell because it just wastes so much space on the board, and it kind of doesn't do much. It's just to keep the clock compared to the rest of the functionality. So in the beginning, I went with the CR1025, which is smaller. This is the CR2032. But the CR1025 has about 10 times less capacity, and actually the typical RTC will only last for about 3 years, which I think is a bit too little. And the CR2032 is actually going to last for 25 years if its shelf life would be past 10 years. So I went with the CR1632 because its shelf life, of course, is also 10 years, but theoretically it can last for up to 13 years. But you do end up saving a bit of space, and it's still a pretty popular coin cell battery. And the software, I used Zephyr mostly because it integrates everything, even though the device has no connectivity or anything like that. But the fact that you can describe the hardware in the like Linux device tree language, I think is really nice. And my favorite feature actually is if you have a modular hardware design. In Zephyr, you can actually describe different hardware modules, and you can describe the hardware interface. Like you can describe a connector, and you can include it in different boards. And during the compile time in the command line, you can basically connect whatever modules you like together, which is pretty convenient. And yeah, I also used LVGL, which is also included in Zephyr, which is quite convenient. And another thing that Zephyr has actually influenced my design is that typically if I would design hardware, I would just choose whatever chips or like integrated circuits like accelerometer or GPIO expander. I would just choose whatever there is, maybe like the cheapest one. But with the Zephyr, it actually changed a little bit, and I started to try to use the same chips that Zephyr has drivers for, because then basically you do the hardware and you get everything else for free. Yeah, and the next thing I want to talk about is the features. And when you have a project like this along your full-time job, you start to feel the lack of time, and you kind of have to have a better control on the features and what you implement. And basically, what I have recognized even more is that every little feature you add is basically, it's very easy to add a feature, but you have to maintain it, you have to test it in production, and it's just a huge maintenance cost. Even the small things like, for example, you can think that if you add like a silk screen for labels on the PCB, that it's nothing, but in reality, if you do new spins, you have to update the silk screen every time, especially if it's a nice silk screen. And in production, you have to test it, right? If you want to maintain high quality, you have to make sure that every board has a proper silk screen, and it's kind of hard to control in an automated way. So yeah, trying to cut down on features is not very easy. And one of the examples I have also is that I've spent quite some time trying to add a software feature for basically when you connect the device, it's recognized as uninterruptible power supply and uses USB power device specification. But later, I realized that it's a little bit too much maintenance for the USB to have it together with the virtual COM port, and later on I decided to remove the feature, which is also was a bit hard. And I also deliberately excluded Wi-Fi and Bluetooth because it's also really easy to add it. Just put SP32 right, but I wanted to have focus on kind of higher quality of hardware and software. Let's say I don't know how much time. Is anyone keeping track of time, or there's no one to keep track? Okay. Um, uh, let's see. Okay, this is an extra thing. I also tried using a e-paper display. I went through several, but eventually I decided not to use it because you can use like this partial refresh, but the user interface still felt kind of, yeah, you can really feel the delay. So I decided to skip it and use the memory in pixel. Another thing I have discovered is that you can actually pretty easily try to do injection molding for the two-component silicone. If you want, for example, to make like a buttons, let's say, yeah, if you want to do this kind of stuff, like if you want to prototype silicone buttons, it's actually very easy. The only thing you have to do is to basically take your part and like make a cutout of like a rectangle or like whatever you call this shape, like a box. And you just need to add like channels to put in your silicone like liquid and some pins for positioning, and you can just get this, and it was extremely easy, and the surface finish is actually it's good enough for like doing prototyping before you order the real thing. Yeah, this is an example of it kind of acts as a display kind of holder mounting solution and the button as well. Yeah. Do you have any questions or?